This is Lab 2, Projectile Motion, by Luxus Hernandez-Celis. The purpose of the lab was to record and observe projectile motion and compare to a calculated computational model that accounted for both drag and one that didn't account for drag. The model utilized for this experiment was a GlowScript-coded model that calculated for net force, velocity, and position based off Newton's second law. And after running the experiment and the computational model, it was determined that the model accounting for drag was far more accurate to observed data compared to the model that didn't account for drag. The model accounting for drag differed insignificantly from the observed data, while the model not accounting for drag reached both a greater height and a greater distance compared to both the predicted model with drag and the observed data. Shown here is the computational model. The computational model was run on GlowScript using the principles of Newton's second law and projectile motion. First, we calculated the net force, which is calculated by adding the force of gravity plus the force of drag. For force of gravity near Earth, we use negative mass times gravity. And for force of drag, we have the equation shown, negative b times mag of ball velocity squared times the normalized ball velocity. And adding this gave us the force net. Secondly, the velocity update formula was used. Plugging in the net force that we previously calculated, we achieved net force over mass times change in time plus the initial velocity. And lastly, the position update formula was used. The first one we used for average velocity, we used the previously calculated final velocity times change in time plus the initial position. And here's a figure displaying the three models. Red represents the predicted model with drag, which we can see is similar to the blue line, which is observed model. And finally, yellow, which is the outlier, is a predicted with drag. For this experiment, the system in the experiment was a paper ball thrown, while the surrounding was the Earth, and the surrounding included the force of gravity and the force of drag. The initial conditions include the paper ball weighing approximately 35 grams and being thrown at a height parallel to the top of the trash can, as this was done intentionally in order to achieve the best parabola. The process simply involved throwing a ball to a piece of paper in an upward trajectory while aiming for the trash can. This process was recorded so it could be reviewed later through the tracker. The initial conditions of the code are starting mass of 35 grams, an initial position of 0.0068, negative 0.027, and 0 meters, and an initial velocity of 1.48, 7.72, and 0 meters per second. When accounting for drag, I utilized a proportionality constant of 0.006. These initial conditions were derived from the observed data. The drag was calculated by multiplying the proportionality constant by the magnitude of the velocity squared and the initial velocity, and the only other force that was accounted for was the force of gravity. Velocity was calculated using the velocity update formula, which is initial velocity plus the net force divided by mass times delta t, and the position was calculated using the position update formula, which is initial position of the ball plus the updated velocity times delta t. Terminal velocity is experienced when the force of gravity is matched by the force of drag, and this would appear on a model like a straight line because the velocity and change in position will be constant. None of our models ever predicted terminal velocity because the graph data was always a parabola. And in order to determine the terminal velocity of an object, we will run the experiment where we drop an object from significant height and find a point where the velocity becomes constant. To answer the second what if question, yes, it would take the same time for the object to reach the floor if we threw it straight down to the ground rather than threw it across like in the original experiments. This is because changes in the x direction are independent of changes in the y direction. And looking at the net force equation, the main force causing the ball to fall is the force of gravity, which is in the y direction, and nothing in the x direction affects anything in the y direction. Now, some possible errors when performing this experiment are inaccurately graphing the trajectory of the projectile in tracker, as those result in observed data being inaccurate. Because the initial conditions of the computational model were determined from the observed data, those would further affect the results of all three models. And another possible error is selecting incorrect initial conditions, as incorrect initial conditions will lead to the data being misrepresented from the beginning. So in conclusion, after performing the experiment, we were able to conclude that the computational model accounting for the drag force was more accurate to the observed model compared to the computational model that did not include the force of drag and the net force. In comparing all three models, the observed data and the predicted data with drag reached a similar maximum height of around 1.8 meters and a distance of around 1.4 meters, while on the other hand, the computational model without drag reached a greater height of around 3 meters and a distance exceeding 1.5 meters, as the force of drag usually works against the force of gravity, so without it, the force of gravity was mitigated. And that concludes this lab. Thank you.